Welcome everyone to our video on balancing redox reactions using the half-cell method. In this video, we are going to use the half-cell method to balance redox reactions in both acidic and basic solutions. You should have some prior knowledge about redox reactions. Specifically, you should know how to identify the two half reactions when given a chemical equation. You should also have some background on ionic and net ionic equations, specifically understanding the process of canceling out spectator ions. Balancing redox reactions is best approached through a series of stepwise processes. Take a moment, pause this slide, and copy down these 7 steps. You'll find it helpful to have the steps in writing in front of you as I'm going through examples. So pause the slide now, and when you're ready, click play again, and I'll flip over to the whiteboard and go through an example. Here's the problem that we are going to solve. Before proceeding, just make a note here that anything with a charge in any of these examples are aqueous ions. Anything without a charge is a pure substance, so a solid, a liquid, or a gas. It won't matter which of those states the substance is in. You just have to note that it is a pure substance and not an ion. Our first step in balancing a redox reaction is to break the reactions up into its two half reactions. In most cases, it is obvious which substances go in which half cell. So it's easy to separate them here. We have a manganese substance, and then we have a substance involving oxygen. If it's not obvious where the two half cells are, that's when it's often more useful to use the other method for balancing redox reactions, balancing by oxidation number. Our next step is to balance all of the atoms other than oxygen or hydrogen. The only other atom in this example is manganese, and there is one manganese on both sides of that first equation. So nothing needs to be done on this step. Our next step is to balance the oxygens by adding waters to the side that needs oxygens. In our first half cell reaction here, the right side needs 4 oxygens, so I add 4 water molecules. The second reaction is already balanced in terms of oxygens, so there's nothing to do. So how are we adding new chemical substances here? Remember, these reactions are taking place in aqueous solutions, which means there is an excess of water molecules available. What we're doing here is just showing that some of the water molecules in the solution are going to be actively involved in the chemical reaction. Our next step is to balance the hydrogens. And the way we're going to do this is to add hydrogen ions to the side that needs the hydrogens. Once again, we are adding a different chemical substance that did not appear in the original equation. Remember that these reactions are assumed to occur in an acidic solution. So that means that we have an excess of hydrogen ions available to be involved in the chemical reaction. At this point, we have balanced all of the atoms, but now we need to balance the charges. So in each half cell, the charge on the left-hand side must equal the charge on the right-hand side. In the first half cell reaction, the left-hand side has an overall charge of 7 plus. The right-hand side has an overall charge of 2 plus. By adding 5 negative charges, or 5 electrons, to the left-hand side, we have balanced the two sides. In the second equation, there are 2 positive charges on the right-hand side and no charge on the left-hand side, so I'll add 2 electrons, or 2 negative charges, to the right-hand side to balance the sides. In a redox reaction, the electrons gained through reduction must equal the electrons lost through oxidation. So we must make these 2 electrons gained and lost equal to each other. So we'll find the least common multiple, which in this case will be 10. I'm going to multiply the first equation by 2, so I'll put times 2, and the second equation by 5. So what I'll do here is multiply every single term, including the electrons, by that multiple. Since we've multiplied the entire half reaction by the same number, we will not have changed any of the balancing that we did in previous steps. Take a moment right now, look at this step. I'm going to clean up the coefficients here just so it doesn't get too messy. Our next step is to combine the two reactions by summing them together, similar to what we've done when you do a Hess's law problem. In this point, we're going to cancel any spectators. So we'll start with the electrons here. On the reactant sides, we have 10 electrons. On the product side, we have 10 electrons. So there's no net change in the electrons. On the reactant side, we have 16 hydrogen ions. On the product side, we have 10. So that means there's going to be 6 hydrogen ions as reactants. I'll write in my chemical substances, and all I'm left with now is 8 water molecules. Before finishing off, we should double check that all of the atoms and the charges balance. We have 2 manganese on the left-hand side, 2 on the right. We have 16 hydrogens on the left-hand side and 16 hydrogens on the right. We have 18 oxygens on the left-hand side and 18 oxygens on the right. So all of the atoms balance out. And then let's look at the charges. We have 6 hydrogen ions, and then we have 2 MnO4s, the permanganate ion, which have a -1 charge. So in total here, we have 4 plus on the left-hand side. And then on the right-hand side, we have 2 manganese ions. So in total, the charges on the right-hand side are 4 plus as well. So the charges balance as well. So that's our check to make sure that we've done things correctly. Let's now look at the process for balancing in a basic solution. If our redox reaction is occurring in a basic solution where there's an excess of hydroxide ions, the first part of our approach to balancing is going to be the same as we did previously. So those first 4 steps up to balancing the hydrogens by adding hydrogen ions is going to be the same. Our next step is going to be to convert those hydrogens into hydroxide ions on paper, and we'll do that by adding hydroxide ions there. So you'll see that these steps in basic solutions are very similar, but we just need a way of having an excess of hydroxide ions, which can be involved in the reaction, rather than having an excess of hydrogen ions. It's important to understand that the steps to balancing is not at all what's occurring in the chemical reaction. This is an algorithm that will lead us to a balanced chemical equation. So take a moment, pause this slide, and copy down these steps. When you're ready, you can go over to the whiteboard and go through an example of balancing in a basic solution. Here is the example we're going to use for balancing a redox reaction in a basic solution. Our first 4 steps are going to be the same as with an acidic solution. We're going to split the reaction into its half reactions. We're going to balance all of the atoms other than hydrogen and oxygen. We'll balance the oxygens by adding water molecules. And we'll balance the hydrogens by adding hydrogen ions. Take a moment, pause the video now, and see if you can do those first 4 steps just like we did in the previous example. Here are my two half-cell reactions. I'll first balance the iodines, and then I'm going to add water molecules, and then I'm going to add hydrogen ions. At this point here is where our process is going to differ because we need to have an excess of hydroxide ions and not hydrogen ions. The way we're going to cancel out the hydrogen ions is to add hydroxide ions to both sides of each half-cell reaction. And for every one hydrogen ion that we have, we are going to add one hydroxide ion. There's 8 hydrogen ions on the left-hand side, so I'm going to add 8 hydroxide ions to the right-hand side. But now the equation's unbalanced, so I'm going to do the same thing to the left-hand side. So that keeps the equation balanced in terms of oxygens and hydrogens. We know that one hydrogen ion and one hydroxide ion can combine to form a water molecule. So we're going to rewrite this as 8 water molecules. Note that we haven't changed how the equation is balanced, but now we have an equation where we have an excess of hydroxide ions, like in a basic solution, rather than an excess of hydrogen ions. Let's simplify this equation now by canceling water molecules. I have 8 water molecules on the left-hand side. I have 4 on the right. So there's a net of 4 water molecules in this reaction. I'm going to clean up this screen right now, just before it gets a little too messy here, and rewrite this in the same way. I've rewritten the equation, haven't changed anything, and now our step is going to be to balance the charges by adding electrons. In my first equation, I have a total of 2 minus on the left-hand side and a total of 10 minus on the right-hand side. So we need to add 8 more negative charges to the left-hand side. In my second equation, I have a total of 2 minus on the left and no charge on the right. So I need to add a total of 2 electrons to the right-hand side. This is a good point to check to see whether you've made a mistake. When adding electrons, if you find yourself adding electrons to the same side of the equation in both half cells, you've made a mistake earlier on. In one half cell, they should appear as a reactant. In the other half cell, they should appear as a product. The final steps are going to be the same as in balancing in an acidic solution. We are going to make the electrons lost equal to the electrons gained, and then sum the two reactions and cancel the spectators. Pause the video right now and see if you can do those steps on your own. And when you're ready, start the video again and see what we get. Okay, here's the process of finishing off this reaction. To make electrons lost equal to electrons gained, all I need to do is multiply the second reaction by 4. So I'll multiply every species by 4, and now the electrons lost equals the electrons gained. Now we can sum the reactions and cancel out any spectators. The only spectators in this reaction will be the electrons, which, as we know, should cancel out, and we can rewrite the rest of the substances in our final equation. And here we have our final balanced chemical equation in the basic solution. And we see once again that some of the hydroxides and some of the water molecules that are present in the basic solution are going to be involved in the chemical change. Note that the atoms and the charges must balance in our overall equation.